It would seem that what could be simpler than light? It leaves no traces, has no rest mass, cannot be compressed, and slips through your fingers faster than you can think. Light is a symbol of freedom, purity, and speed. It flows through the universe like an eternal wanderer and never stays in one place for long. But it turns out that even light is not as elusive as we thought. In recent years, scientists have begun to create something absolutely unimaginable from photons. They have cooled them to temperatures at which the laws of physics, as we know them, simply cease to apply. For the first time, light has been stopped, condensed, and transformed into matter, but not into some abstract mass, but into a super-hard crystalline state that behaves like a liquid at the same time. Light can now flow like water, but remains as hard as a diamond. This paradoxical form of matter radically undermines the very concept of hardness. It reverses the classic boundaries between wave and particle, between energy and matter. Yesterday, this would have sounded like crazy science fiction. Today, it is hard scientific fact. This is not just a laboratory miracle. It is a completely new state of matter. Perhaps this is only the tip of a giant iceberg, an iceberg made of light. At first glance, it seems that forcing light to behave like matter is a task for gods, not humans. However, several teams of scientists, including those from MIT and the Max Planck Institute of Quantum Optics, have achieved what until recently was considered pure impossibility. They have created quasi-matter from photons that both flows and retains a crystalline structure. But how? After all, photons, as we know, do not interact with each other. They are free as the wind, neither repelling nor attracting each other. To transform them into matter, the scientists had to use a trick bordering on scientific alchemy. They placed the photons in a special cryogenic chamber, cooled to practically absolute zero, where thermal fluctuations disappear and quantum effects come to the fore. They then directed the light into an optical cavity filled with a special type of atom, usually rubidium or yttrium, cooled to extremely low temperatures by lasers. And this is where the real magic begins. Under these conditions, photons interact with atoms to form polaritons, hybrids of light and matter. It is these exotic quasi-particles that begin to sense each other, attract each other, and arrange themselves into a network, like molecules of a substance. This is no longer a simple stream of light. It is Einstein's condensate of light, in which photons lose their individuality and behave as a single coherent whole. This is where this super-hard liquid state is born. Photons are enclosed in a crystal structure, but they can move without resistance, like a non-viscous liquid, like a superfluid. This is a completely new class of matter in which the boundaries between phases are blurred and physics begins to sound like poetry. Such a discovery is not just an effective demonstration. It is the first revolutionary step towards fully controlling light as a building material, where it will be possible to form it, remember it, give it shape and density like clay. But at the level of elementary particles, it sounds like a crazy oxymoron. Light and suddenly super hardness? Where is the logic here? After all, light is movement, vibration, pure energy. How can it be compressed, preserved, forced to retain its shape? And here is where the strangest thing begins. In everyday life, hardness is resistance to deformation. Metal, ice, and diamond do not succumb to external pressure. However, physicists went further and introduced the term super-hard state, in which matter, and now even light, simultaneously maintains internal order and exhibits properties similar to those of a liquid. This means that it has the structure of a crystal but behaves like water without friction. There is nothing crazy about this. It is simply quantum reality. When photons switch to the polariton mode and enter the Einstein condensate base, they lose their individuality and begin to move as a single wave, simultaneously sensing each other and arranging themselves into a structure. A kind of lattice of light is formed, but not a static one, but a fluid, malleable, and flexible one. It is this behavior that scientists call superhardness, not in the sense of mechanical strength, as in the case of titanium, but in the sense of internal stability against movement. Physicists saw for the first time how photons in this state form regular, quasi-crystalline patterns. What's more, these patterns behave even with weak external interaction. Light seems to have learned to maintain its form. It is no longer a stream, a flash, or a reflection. It is a structure that can be measured, observed, and even used as an element to create other forms of matter. And here's what's really cool. This hardness does not interfere with the movement of light. It does not slow it down. It is like the perfect material, devoid of friction, resistance, and wear. No atomic crystal can achieve this. Simply put, scientists have learned to give light shape without turning it into matter. Light remains light, but now it obeys the laws of solids. At first glance, this is a pure contradiction. How can something be hard, i.e., retain its shape, and at the same time flow like water or mercury? In the ordinary world, this makes no sense. But we are no longer in the ordinary world. We are in quantum reality, where paradoxes are not mistakes but rules of the game. As we already know, the state observed by scientists is called the superhard phase, a quantum anomaly in which matter, and now also light, behave simultaneously like a crystal and a superfluid. It is not simply solid, but regularly organized, with a symmetrical internal structure, like a snowflake under a microscope. It is this phenomenon that baffles even physicists themselves. In classical physics, solidity and fluidity are incompatible. But in quantum physics, the opposite is true. Some states of matter, especially at extremely low temperatures, escape the control of known logic. They are no longer subject to Newton's laws. They are subject to the laws of superposition, non-locality, and collective particle behavior. In 2024, in laboratories where superhard light was obtained, scientists noticed one surprising thing. Photon lattices flowed through the trap, but the form of the lattice itself remained unchanged. That is as if a glass cube filled with mercury were tipping over. The mercury flowed, but the walls of the cube remained just as distinct and regular. Some compare this to flowing crystals, such as liquid crystals in screens, but here everything is much deeper. No classical materials are capable of such behavior, especially when it comes to pure light. We are not just talking about the strange behavior of matter, we are talking about a new phase of existence that no one could have imagined before. And now pay attention. It is precisely this behavior that may become the basis for the materials of the future, where the structure remains intact under any load, and movement inside occurs without energy loss. If you think that transforming light into a super strange substance is already crazy, wait, don't rush. It's worth looking a little deeper, and a strange, literally extraterrestrial level of physical reality will open up before us. We are talking about time crystals, or, as they are also called, time crystals. What are they anyway? Imagine an ordinary crystal. It is characterized by spatial symmetry, and the atoms in it repeat at specific intervals. Now reverse this concept. A time crystal is a system in which states repeat over time, as if frozen in the rhythm of a heartbeat. It is a quantum reality in which time is structured. So scientists working with superhard light structures began to notice that the behavior of photons in a trap is not only organized in space, but also begins to repeat itself in time with absolute regularity, like a clock, only at the quantum level. This is what a time crystal is. Time crystal photons are not just a theoretical toy. The Google Quantum AI group demonstrated a time crystal on the SE-Core quantum processor. And after just a few years, similar properties began to appear in superhard light systems. This means that the light in the trap is not simply enclosed and ordered, but dances in a precise, infinite rhythm, without energy loss and without outside interference. It is a state of imbalance but stable. It exists outside of time, outside of classical thermodynamics. It is precisely such structures that can become the basis of quantum memory, in which information will be stored not in space but in time itself. No external interference, no aging of matter will be able to erase it, because the carrier will be a repeating quantum state of light, in which each photon pulse is an unchanging sign. Light becomes solid and fluid at the same time, and within this stream a rhythmic structure is born that does not disappear with the passage of time. It is no longer just a substance, but a form of movement that has become stable, a quantum ornament in space-time. And who knows, maybe such structures govern the deeper levels of reality that are currently beyond the reach of our devices. Perhaps time crystals are those more complex dimensions in which matter and energy are only vibrations in the rhythms of incomprehensible quantum symphonies. Matter has three states: solid, liquid, and gaseous. Later, a fourth was added: plasma, a heated soup of ions and electrons. But what about light? All our lives, we have perceived it as something unchanging, a wave, a particle, a quantum, formless, immaterial, intangible. But now that scientists have forced light to solidify and flow like a liquid, this paradigm is beginning to crack at the seams. Can light have its own phases, its own states of matter? And if so, how many are there? One, two, or maybe five? Currently, at least four potential states of light are actively discussed in scientific circles. Ordinary light is a stream of photons flying in a vacuum. It is the form of radiation we know, which has no mass and moves at the speed of light. Polaritonic fluid, in which photons in a material combine with environmental excitations, transforming into quasi-particles. This is no longer just light, but something between light and matter. Einstein's base photon condensate, when photons slow down, cool down, and begin to behave as a single quantum whole, losing their individuality. It is almost a quantum substance, a super-hard state of light when crystalline order and fluidity appear simultaneously in the system. And now the discussion about the fifth state of light is beginning, unofficially but already seriously. Its working name is topological light. And this is not just a new phase transition, but a fundamentally different behavior of light when its properties do not depend on the environment or temperature, but on the global structure of the field. Imagine that photons in such a system move along closed quantum paths, bypassing obstacles, without losing energy, and without even succumbing to local changes in the environment. It's as if water were flowing upstairs, simply because that's how it's written in its topology. The super-hard state may be a bridge to this fifth state. There are already first experiments in which light in a trap exhibits topological stability. It does not scatter. It does not change shape, as if it remembered what it was supposed to be. What next? Who knows? Perhaps the sixth state will be holographic, where light will unfold in the projection of a hidden dimension, or dark, associated with matter that we cannot yet sense. After all, we can already see that light is not just radiation. It is a multi-level quantum substance with a potential that is only beginning to reveal itself. With each new discovery, it becomes clear. Light is not what we thought it was. It is not just a carrier of information. It itself becomes a form of matter, structure, memory, and perhaps even consciousness. And now the real intrigue begins, because whatever the case may be, every exotic state of matter, be it super-hard light, time crystals, or polariton fluid, must be subject to the laws of gravity. And that means that if light becomes something material, even in a quasi-sense, it comes into play with the fundamental force of the universe. But the question arises: gravity is classical and light is quantum. How can they be reconciled? Some theorists have already looked into the abyss and asked, if light in a super-hard state creates stable quantum structures, can it locally curve spacetime? The answer is frighteningly logical. Yes, it can. What's more, such light configurations, being stable, can create quantum pockets of curvature. These pockets are miniature, temporary, but theoretically can affect other fields. This means that light, when solidified, can become gravitationally active. Within loop quantum gravity, where spacetime itself consists of discrete loops, stable light crystals can act as nodes that fix certain states of geometry. They can be markers of the quantum topology of the universe, not as stars, but as structural threads of space itself. This may sound complicated and frightening, especially if such structures can move. It means that light can not only flow, but also carry curvature with it. And what does string theory say about this? In string theory, particles are vibrations of fundamental strings. Photons are simply a specific type of vibration. But if we create a stable, closed vibration, a kind of standing wave of light that does not disperse or disappear, then it is already a new resonant object. Some physicists suggest that stable light configurations may be projections of holographic structures from higher dimensional space. And if that's true, then super-hard light is literally a shadow from another dimension. Not only does it exist, but it tells us something more. And now for the craziest idea. What if light in these states is not energy, but a geometric phenomenon? That is, what we previously called a photon, under exotic conditions, turns into a pulse of pure geometry, appearing and disappearing at the microscopic level of spacetime. This is consistent with the hypotheses that energy and mass are only a curvature of the field, not a substance. Then the super-hard state of light is simply a form of a stable bubble in the fabric of the universe. When scientists first obtained hard light, it seemed that this was the limit. However, as the history of science shows, there are no limits. If photons can take on the characteristics of matter, structure themselves, form crystals, and even flow, then the question arises, can something else become light? And this is not just a play on words, information as light. Some theorists working within the holographic principle assume that all matter may be a projection of information. If so, matter is recorded light, energy frozen in space. The body, metal, wood, all of these are simply different forms of organized light. This is also consistent with the idea from quantum field theory. Everything we see is the result of the interaction of fields in which photons act as messengers. If we learn to redistribute fields, we may be able to transform not only light into matter, but also all matter back into light. Thoughts as frozen radiation? This may sound esoteric, but experiments are already being conducted in the field of neurophotonics, in which the brain itself emits weak photons, so-called biophotons. Some scientists are seriously discussing whether thoughts are a form of organized light within the biological system. If it is confirmed that biophotons participate in cognitive processes, it will not only be a revolution, but a shift towards neurolight, and perhaps even information light, a carrier not only of energy, but also of meaningful signals. Space can be light. One of the most non-trivial hypotheses in quantum gravity states that space and time do not exist on their own. Space and time do not exist on their own, but arise from a network of connections consisting of light or something very similar to it. In spin network models, space consists of qubits of geometry that can connect in the same way as photons in a laser in terms of phase, direction, and frequency. In this sense, space itself is closed light that retains its shape. What about consciousness? Integrated information theory posits that consciousness arises when information organizes itself into a closed structure with a certain degree of complexity. And if this structure, as experiments have shown, can be expressed through photon fields, then it turns out that consciousness is a form of light, self-aware. Quantum mechanics, the holographic principle, and even neurobiology, all of them converge in an unexpected way at one point. The division between light and matter, mind and energy, is not so absolute. Perhaps we just haven't learned to look properly. What if the entire universe is a huge collection of organized light, and we are its temporary structures, nodes, flashes in the matrix of photon fields? And then the question is no longer what else can become light, but what in this reality is not light at all.